Okay. I think we're ready. So today we're going to be covering (3.6) which is hyperbolic functions, and then on Tuesday I would be prepared for potentially your first quiz of the semester, which would be where you walk in, you take a quiz, right? All right, so and that quiz could cover anything that we've talked about. So 3.5 or 3.6. And there is potential today for us to actually get into 4.7. So maybe here today, 4.7. And I realize that you probably don't want me to rush through the class, but I can assure you that you will be hoping for more time later. And if we can get this easier stuff out of the way first, we can have more time, when the stuff starts to get a lot more challenging. All right? Let's see. Any more paper? Here we go. Everybody has their little thing. So what I'd like for you to do is to not lose this and bring that back, put it in your folder or whatever, and just bring it every class and set it up on your desk, and then I can hopefully learn names. At the minimum, I'll be able to say Ivana, right? And then it'll go better than me saying nothing at all, all right? Okay, 3.6. So how many of you actually printed out the notes for 3.6? 2, 3, that's it. Now these notes are in Canvas, right? In Canvas, these are all there for you. You can print them out, you can bring them to class. All right, so I would expect that if you want to follow along and write on those things, you do that. All right. I also need to take attendance today. So look at the sheet I'm going to hand out. I want you to initial down the column that represents today, which is the 27th of August. There's 2 yellow boxes, green boxes. Those are students who have not completed the required quiz that is in Canvas. So if you have a green box, that means you still need to do something online. And who is that? Ronald and Alexis. Alexis, we talked? You did it already? Okay. So, Ronald, where's Ron? Yeah, we talked. You did yours? Yeah. No. There's Ron and there's, but yours, yes. What's your last name? Okay, so that's the Ron I'm talking about. I know you're not, but you also weren't on my roster. What's your last name? Oh, you're here, but when I checked it today, I don't know, I'll double check it. Okay, so I'm going to pass this around. Please make sure you initial. All right, let's get started. 3.6 hyperbolic trig functions. And I think I'll make this a little smaller so we can see it here. Thank you. That should work. And for my internet students, I'm going to go ahead and move this over so that they can see this also. So last time we talked about the inverse trig functions, didn't we? The inverse trig functions. And we talked a little bit about their domains, and then we said that there were derivatives. And in the homework, you got to kind of play with that a little bit and get a feel for how the derivatives seem to always spit out things that are like square roots, or that spits out that 1 over 1 plus x squared, right? There was also a problem where you were asked to actually derive the formula for the inverse cosecant, I believe. And so you had to follow the method I did in class. All we're doing today is we're introducing another set of trig functions. There's 6 of them, and talking about their derivatives, and then their inverses, and their inverses derivatives. So we're actually going to gain today 12 new functions with 12 new derivatives total. So what is a hyperbolic trig function? Well, the 6 hyperbolic trig functions come from putting this together, e to the x and e to the negative x. We know that e to the x is an exponential function, right? We know e to the negative x is also an exponential function. They look different, all right? E to the x does what? Exponential, I'm going to come behind you real quick so I don't have to move the camera. E to the x looks like what? If I graph it. Okay, yes. Goes like this. That's e to the x. And e to the negative x is a reflection of that over which axis? The y-axis. So this is e to the x, and e to the negative x looks like that. And so it turns out that in different branches of science, these two functions a lot of times come together in one, we combine them into one function and use them a lot. And because of that, because the special combination of those two functions, we actually have definitions for certain ways of combining them together. So you want to look at these are like kind of like the two parent functions, and depending on how you put them together will determine what is called the hyperbolic sine function or hyperbolic cosine function or hyperbolic tangent, so on and so forth. But they're all combinations of just those two functions. All right, so that's where this all kind of comes from. And the definitions are pretty straightforward. I mean, there's no craziness here. The hyperbolic sine function, or you could say the sine hyperbolic function. I've heard it said both ways. Technically, I believe you're supposed to say hyperbolic sine, but when you're reading it from left to right, you might say like sine hyperbolic, and that's okay. So sine hyperbolic of x is equal to e to the x minus e to the negative x divided by 2. Or you could also take the 2 off the bottom and pull it out in front and write 1/2 times e to the x minus e to the negative x. I believe in your notes I did not include this, right? I did not include that in blue, so that's something you could add on there. Either way, you can look at hyperbolic sine as one of these two expressions. Now, the only difference between that and cosine hyperbolic is what? There's a plus between the two parent functions, those two e functions. And then everything else, the other 4 hyperbolic trig functions, all come from our standard definitions from our original trig functions from pre-cal. Tangent in pre-cal was sine over cosine. Well, same thing here. Hyperbolic tangent is hyperbolic sine of x divided by hyperbolic cosine of x. So same thing that you normally, I guess, would think when you think tangent. The hyperbolic cosecant function is 1 over the hyperbolic sine function. So that's exactly the same as in pre-cal. The hyperbolic secant function is 1 over the hyperbolic cosine function. So it's just reciprocals, right? That's all it is. And then the hyperbolic cotangent function is the reciprocal of the hyperbolic tangent function. Just flip those 2 over. All right, got it? All right, now what do these things look like? Right? What are the graphs of these? So let's take a look at these graphs. I'm starting out with the hyperbolic sine function. Does that look anything like the sine function from pre-cal? Not at all, right? That doesn't look anything like the sine function. It's not periodic, is it? Like the sine function was periodic. This one doesn't appear to be periodic. This almost looks like a cubic function, like going down on the left and up on the right. That's almost what it looks like. But it's not. It's some combination of e to the x and e to the negative x, so that when you combine them a certain way, you get that graph. Good, thank you. All right, and let's now look at the cosine hyperbolic function. You think they're going to look similar? I mean, sine and cosine looked similar in pre-cal, right? Think that sine hyperbolic and cosine hyperbolic will look similar? You would think, right? Not even close, okay? Not even close. I mean, it is kind of close. It's kind of reflected up, but it looks more like a what? It looks more like a parabola. Can we kill just the lights over here? Just see if, yeah, that'll work. That green doesn't really come out that great. Okay, so it almost looks like a parabola, right? But it is not a parabola because it involves e, right? So it can't possibly be a parabola. Parabolas involve x squared. So it's not the same thing. Let's look at tangent hyperbolic. Wow, that almost looks like 1 over x, doesn't it? Pardon? Oh, did I hit that? Oops, that's what I meant. That almost looks like what from pre-cal? Anyone remember which one looked like that in pre-cal? It's like a sideways tangent. It's like the inverse of tangent, almost. But it's not. Yeah, you could almost say it's like a cubic function, or cube root function, or something like that. Okay, so but the point I'm trying to get at here is that if you look at all of these hyperbolic trig functions, they all have very, very different characteristics than what we're used to seeing with the trig functions from pre-cal, right? In pre-cal, they were all connected to each other in some way, and you could kind of get the graphs by just investigating sine and cosine. So those are the graphs. The one that we are actually going to look at later in the class is the cosine hyperbolic one. This one is actually pretty interesting. All right, so the first example here is I'd like for us to be able to show this identity. So we want to be able to show this identity. Boom, boom, boom. Yeah, that'll work. So this identity that's up here, when it says show something, that means you have to prove it's true, right? You have to prove that that is a true equation. Doesn't that look very similar to this? One of our favorite identities from pre-cal? Didn't that thing, that identity right there, didn't that bail us out a lot whenever we see like sine squared something plus cosine squared something? We say, oh, but that's 1. So we use that a lot. This identity is different, right? It involves the square of both the cosine and the sine hyperbolic functions, but there's not addition between them. It's subtraction. And because subtraction doesn't commute, the order is important. If you put the cosine hyperbolic squared in front, subtract the sine hyperbolic squared, then we should get 1. So I want to show this. Cosine hyperbolic of x squared minus sine hyperbolic x squared. I want to show that that's 1. So what I need to do is I need to start on one side and turn it into the other side. So I'm going to start with the left side and show that I can turn that into 1. All right? Questions? Now you will not have to constantly prove these identities. There's a bunch of them, and I'll show them to you. Well, they're right. You can start to see them right there. There are important identities with the hyperbolics you need to know. I'm just showing you how you could prove one of them. And then you could do it as an exercise. You could go through and do those yourselves. So how would we do this? Well, let me first start by rewriting this. But instead of writing cosine hyperbolic x, let me actually write down what cosine hyperbolic x is in terms of e. And then the squared here means square the whole thing, right? So what is the cosine hyperbolic x? It's e to the x plus e to the negative x all over 2, right? So I could, and then I'm going to square that. So it's e to the x minus e to the negative x, the entire quantity, or yeah, that entire quantity divided by 2, and then square the whole thing. Plus, oh, sorry, oops. This one is the opposite, over 2. You can remember it by what the sign has the subtract on it, right? Sign has subtract. S, subtract, sign. Okay. All right, so now we have the pleasure of squaring these. All right? And even though it looks pretty bad, it's going to be real nice in the end. It's going to turn out to be 1. But let's just see the math behind that. So when you square a fraction, you square the top and bottom, right? Squaring the bottom is easy. It's going to be a 4. That's going to be a 4 over there. But on the top, I'm going to actually have to multiply this times itself, right? This times itself. Okay, so I'm going to get a new line here. I'm going to put e to the x plus e to the negative x times itself, e to the x plus e to the negative x, all of this over 4, minus e to the x minus e to the negative x times e to the x minus e to the negative x, all over 4 again. So I haven't actually squared it. I just wrote it out so that I could actually do the multiplication now. And then we get to expand those, or if you like, the FOIL thing. So what's e to the x times e to the x? E to the 2x, right? E to the x times e to the x is e to the x plus x. You add the 2 exponents together. X plus x is 2x. So this first multiplication gives me e to the 2x. What about the next multiplication? Careful. 1. Exactly. E to the x times e to the negative x is e to the x plus a negative x, right? Plus a negative x. That's 0. E to the 0 is 1. Understand? E to the 0 is 1. So the second multiplication we get through here is going to give us plus 1. Yes? Okay. I'm sorry if the camera's getting in the way, but if it's really bothering you, just try and move your table so that you can see. Next thing, inside, what's that going to be? 1 again. So plus 1. And then what's the last multiplication? That'll be negative 2x, e to the negative 2x. Because you have negative x, you add them together, you get negative 2x. So this will be plus e to the negative 2x. All of this over 4. Minus. Now do the same game here. The only difference is that we have minus and minus there, right? That's going to change some things here. The first multiplication I get is still e to the 2x. What's the next one? Minus 1. Because this is a positive term and a negative term. So you get negative 1 here. What about the middle one? Minus 1 again. So here. Are y'all following me or no? Yes? Okay, and then finally, plus e to the negative 2x, all of this over 4. And a lot of stuff's going to go away. I can put these together, can't I, into one fraction because they both have the same denominator. So if I do that, I will have e to the 2x here plus 2 plus e to the negative 2x. And now I need to go and subtract everything I see up here, which is going to change the signs of everything, right? So instead of writing down e to the 2x, I'm going to put minus e to the 2x. And instead of writing down negative 2, I'm going to write down plus 2. And instead of writing down plus e to the negative 2x, I'm going to write down minus e to the negative 2x. And all of this divided by 4. And do we get things to go away? Yes. You got e to the 2x, right? Take away e to the 2x. You have e to the negative 2x. Take away e to the negative 2x. 2 plus 2 is 4. 4 over 4 is 1. So we have proven the identity. All right, and this would be kind of equivalent to like the Pythagorean identity, the one I started with, but for the hyperbolic trig functions. Questions? You could set up the others. You could set up all these the same way. You could start with one side and try and turn it into the other. And I believe I'm going to do this one. Not right now? Yeah, not right now. I'm going to do this one, though, in a little bit. Okay? Oh, you know what? I think I'm going to do it now. Yeah, let's do it now. I'm going to do another identity. This one's kind of fun. All right, it's time for me to start calling on people. Are y'all ready for that? Does everybody feel nervous? Okay, I'm going to try and show this. Kiki, did you say you wanted to go first? Is that what I heard? No. I thought that's what I what I just heard from you. Okay, I misheard. Geez, what am I doing, Robert? All right, that's the last one, right? There we go. All right, so this one I'll ask a volunteer. Can anyone tell me what formula this is like from pre-cal? Yeah, it's like you're thinking double angle formula. There's also on your formula sheets usually something called the sum and difference formulas, like sine of x plus y, sine of x minus y, cosine of x plus y, cosine of x minus y. This is similar to that. This is a sum formula for the hyperbolic cosine function. And according to the formula, that's what it is. So we need to show that that's true. So let's see here. Luke, I like the name Luke. So do you remember when you're trying to prove something like in an equation like this and you're trying to prove it? I already said you have to start with one side and go to the other side, turn it into the other side. Do you remember at all which side you usually want to pick? The easier looking one or the more complicated one?
I don't remember.
Don't remember? What's your instinct? The easier one to turn it into the harder one? Okay? Yes?
It's the more complicated one because it's easier to squish something than try to expand on it.
Now, it can go both ways. I mean, you can actually start with either side, but it's usually easier to start with the harder side because if I start with, just imagine if I was trying to show this. What if I was trying to show the Pythagorean identity, right? And I said, I'm going to start with the easier side. There's a lot of things I can do with one, right? I can make one from a lot of things. So it's harder for me to get from here to here than it is for me to go from here to here. Here I'm kind of forced into a certain lane of the highway, so to speak. And so we like to generally go with the harder side. So Luke, now you know that? No harm, no foul. All right. So the harder side then is going to be which side? The right side. Okay, the right side. And I need to make the right side turn into the left side. Now, just so that we know where we're headed with this, I'm going to pick on people I don't know because I know some of you. Kelly, all right. Can you tell me what this is in terms of E? So convert the left side, which is the side we're trying to get to. Can you convert that to the E formula instead? Yes, that formula. How would that formula be written for this, though? Because you don't have cosine hyperbolic of x, you have x plus y. So any idea what you would do? Let me help you. Squint your eyes and call that whole thing u. What's the formula replacing x with u? What would it be? E to the u. So for us, u is what? And then, was it plus or minus? Plus. Yes, it would be e to the negative x plus y. How should I write that? Is that okay to write it like that? Parentheses around the x plus y. See? And then divide by 2. I'm going to put the 1/2 in front. I want you to see that. Okay? Does everybody see how this hyperbolic cosine of x plus y is actually this? Just it's taking the formula and replacing the x in your formula with x plus y instead. Yes? That's what we need to show this is. Okay, so that's where I'm going to try and make that. I'm going to try and make that turn into this. Understand? If I can do that, then I can go back and say, well, that's cosine hyperbolic of x plus y. Any questions? All right, so keep that in mind. I'm going to erase it. That's where we're headed. Now, I'm going to start with the right-hand side of the equation. RHS, right-hand side. And at the end, I better get my very last statement will say this, left-hand side check. That means that I've worked this out and turned it into the left-hand side of the equation. Ethan? Sir. All right. I need your help to convert this entire expression in terms of e. And I'd prefer if you do it with the 1/2 things in front, not the 2 on the bottom. Okay. Okay? So I'm just going to listen to you, and I'm going to write. Now we're here. Yes, you're good.
Yeah. 1/2 times e to the y plus e to the negative y.
Good.
And you're adding to that e to the x.
1/2. Yes.
Sorry.
It's all right.
E to the x minus e to the negative x. Multiplying that by 1/2.
Yep.
E to the y minus e to the negative y.
Anybody have any questions? It's just rewriting the formula for each one of these 4 pieces, right? And making sure we get the additions in the right places. Ron? What do you want to do, Ron?
Well, first of all, I want to get all the 1/2s on.
You pull the 1/2s? Okay, so how do you want me to do that? You want me to go these 2 1/2s together?
Yeah, those 2 1/2s together and the other 2 1/2s together.
So 1/4, 1/4? Okay. All right, let's see, Ron. I'm going to challenge you here.
Or we could just do a bracket on.
On the outside of everything?
Yeah.
I'll do that in the next step. If you're there, that's good. So Ron's decided 1/2, 1/2 is 1/4. And then Ron's going to do this times this mentally, and it's going to be pretty remarkable. Right? Because you're going to multiply this times this now, right? You want to multiply this times this?
Yeah.
Okay. So I'm forcing Ron to foil this. This times this, what's that, Ron?
E to the xy.
E to the
X plus y.
x plus y. Okay, so let's make sure we're all aware. Remember, we have the same base. So you put them together, you add the exponents, so you get e to the x plus y. Now remember where we were supposed to go with this, right? Didn't we have that in there somewhere? So it's looking promising that this is going to lead us there. Okay, that's just the first multiplication. Now we do this times this. You want to keep going, Ron?
Yeah.
Okay.
X minus y.
So what do I put here? Plus
Sorry, e to the x minus y.
e to the x minus y. Everyone still aboard? And we got to keep going. There's going to be 4 of them here. So
Plus e to negative x plus y.
good.
Plus e to negative x minus y.
There we go. I agree. Close the parentheses. Okay, now I'll stop, Ron. You've proven yourself already. All right, so that's just the first group here. Now plus 1/4. Again, putting the 1/2s together. Same principle, so let's see. Got that table, got that table, got that table. Know the people there. So that only leaves this table. So I'll let you volunteer. Anyone want to volunteer to multiply this one out for me? You want to do it? All right. So what's the first You're going to do here to here now? Okay.
e to the x plus y
E to the x plus y
minus
minus, good, because it's a positive times a negative, so minus, go ahead,
e to the x minus y
x minus y
minus e to the minus x plus y plus e to the x minus x minus y.
Good. So that's the same foiling thing happening there, right? Everyone agree? It's kind of fun, isn't it?
Plus the x.
Now, I'll pull the 1/4 out, Ron. Okay, 1/4 is going to come out of everything. And then it'll just be all of this, right, plus no 1/4 all of this. Yes? So, see if we can do it without having to kill ourselves here. What do we get? Tell me about this one. I have two of those, don't I? Remember, the 1/4's gone, right? So I have one of them over there. I'm going to add to it another one. 1/4 is not here. The parentheses can actually go away because we've taken the 1/4 out. Trying to save myself from having to write this whole thing over again. So I've got two of these, right? So I'm going to put 2 e to the x plus y's. Okay, that takes care of those. How about e to the x minus y? That one here and this one here cancel each other out. So those are gone. And then same with the next one, right? E to the negative x plus y. Here's another one, minus e to the negative x plus y. Those cancel each other out. They're gone. And then the last thing I have is 2 of these things, right? 2 of these. So I put plus 2e to the negative x minus y. What can I pull out of both of those? A 2, and it comes out with the 1/4 and becomes 1/2. And then I'll turn my bracket into parentheses. E to the x plus y plus e to the, factor the negative out, minus x plus y. Since these are both negative, just pull a negative out right here, and then it turns into negative in front of the x plus y, and that's exactly what we wanted, wasn't it? So now from this point, we say this is equal to cosine hyperbolic of x plus y, which is the left-hand side, right? There we go. So it's manipulation, right, of these things and being comfortable with these exponential functions and messing with them. All right, good. Moving along. Well, since we have six new trig functions, right? We get to take derivatives of them because we love derivatives. Right? So these are the formulas. These are on your formula sheets, your 6 sheets, right? Do these resemble the formulas from Cal 1 in sine and cosine? If I asked everyone when we walked in day 1, what's the derivative of sine of x, everyone would say cosine x, right? If I say now, what's the derivative of hyperbolic sine of x, everyone says the same thing, right? Cosine hyperbolic x. But in Cal 1, the derivative of cosine of x was negative sine x, not with hyperbolics though. Hyperbolics, it's not. But it is sine at least, so we can be that, we can be happy with that. Hyperbolic sine. So do you see the similarities? If you were to look at these next to the traditional trig functions, they would all be connected, but the signs are different on some of them. And some of them they're the same. All right, so you need to know these derivatives, or know where they are on your formula sheet at least. You should at least know the first three. You know, have those in your memory bank, because that's kind of like what you were expected to know in Cal 1. And I believe the next thing we're going to do is actually prove. Oh no, we're going to take a derivative. So we're going to do this one right here. If y is equal to x, hyperbolic secant of e to the x, find y prime. So I just put the derivatives up there, didn't I? I just put them up there for you. So you don't have to go and prove those derivatives. We can now just use them. But I will take a moment before I do this problem. I'm just going to show you real quick. I'm just going to show that the derivative of sine hyperbolic of x is equal to cosine hyperbolic x. I'm going to show that to you real quick, because this one goes really, really fast. So what is sine hyperbolic? The definition of it. It's 1/2 e to the x minus e to the negative x, isn't it? So I want the derivative of this. The derivative of that, what do I do with the 1/2? Just leave it out there, okay, 1/2. And then now I'm going to take the derivative of what's in here. So let's see here. Chris? Derivative of e to the x is e to the x. Staying with Chris, I'm going to have now minus the derivative of e to the negative x. So e to the negative x times negative 1 times negative 1. So you have to use chain rule when you get to this one, right? Because derivative of e to the x is itself times derivative of what's up here, which is derivative of negative x is negative 1. So just to remember that pops out there. And that's it, right? Done? And what does this negative do to that? Changes it to plus. And what is this? That's your cosine hyperbolic of x, isn't it? So all that happened was it changed that minus right there into a plus at the end of the day. That's all it did by taking the derivative. So you got the cosine out of it. That's kind of cool. All right, so let's do one more. Let's do the tangent one. I think that would be, the tangent one might be a fun exercise for you to do. Like, you know, y'all work on it together in groups. See if you can show this. And I'll only give you about, I don't know, 7 minutes or so. See if you can actually show that the derivative of tangent hyperbolic of x is equal to secant hyperbolic squared x. And I know you're going to probably run into some issues with this. So let me just remind you what this means. This means 1 over cosine hyperbolic x squared. Isn't that what secant hyperbolic x means? And what is cosine hyperbolic x? 1/2 e to the x plus e to the negative x, right? Then squared. So, I mean, that's cosine hyperbolic x, but squared. So what you have to do is you have to go here and start with this, right? Write down what you think tangent hyperbolic x is in terms of e. Then take the derivative, all right, and then show it's that. Let's see if y'all can get anywhere with this at all. You want the definitions? There you go. I'm going to help you because I know some people are going to get hung up. Sine. All right, that's what I'm going to give you as a hint. That's where you start. All right? This is tangent hyperbolic. It's sine hyperbolic over cosine hyperbolic, right? What happens to the 1/2s? Cancel. Then you need a derivative. How do you take a derivative of something like this? Quotient rule. Have fun. You basically need to do quotient rule on that. Pay attention to your signs. It'll actually work out decent. Y'all can talk to each other. You know, I'd like, if you need to assist each other, that's okay. If anyone needs a hand, just raise your hand and I'll come by. F prime g minus g prime f and minus g squared. It's different ways that people learn it. All right, bring it back to the surface. Quotient rule right there. A version of it. Wasn't there a bonus due today? No? Did I give y'all a bonus? No, wrong class, sorry.
Right there.
While you're working it out, I am going to actually start working it out myself. And so you can kind of look up and see if you're getting the same thing. Does anybody feel like they're getting somewhere with it? Yes? A couple of you? Yeah? I'll give you about another 2 minutes to see if you can get there. Is that where you got? Okay. Is that what we wanted? Okay, sort of. There's a way. There's a way. I think that's good. I'm going to just talk through it real quick. So here's what we've got. Tangent hyperbolic was sine hyperbolic over cosine hyperbolic. We canceled the 1/2. Quotient rule, right? We have a top function, a bottom function. The derivative of a quotient is the derivative of the top function times the bottom function minus the derivative of the bottom function times the top function all over the bottom function squared. Depending on how you learned it, you may have learned that these are backwards and these are different. Just depends on your instructor. But at the end, we multiply it all together. We should all get the same thing. So this little prime mark means I need to take the derivative. That's my next line. I take the derivative of e to the x minus e to the negative x. So derivative of e to the x is itself. The derivative of, and let me cover up the minus, derivative of e to the negative x is e to the negative x times -1, chain rule. So the negative is going to pop out and hit that and make that a plus, so we're going to have this. Then the second factor is the same. We come over here minus, minus, now we take derivative of this, and what happens is basically the sign there changes. So we get this. And then that's exactly what we have next to it also. Then all over the bottom squared. So does anyone have a question on that? The next step is actually foiling these two together. So e to the x times e to the x is this. E to the x times e to the negative x, we did that already. That's 1. The middle ones also give you a 1. Then the outer ones give you this. Then you do the same thing over here, minus, and then figure out what all this is. And that's this line right here. Then you have to distribute the negative through, and good things happen, things cancel out, and all you're left with is 4 up there. Do y'all follow that? The 4 being on top of this? Is that the answer we wanted? Not quite. What we wanted, what were we trying to get to again? It was 1 over 1/2 e to the x plus e to the negative x, right? But all of that squared, right? All of that squared? Well, if I squared this, wouldn't you have to square the 1/2? Yes. And that would become a what? A 1/4. And isn't a 1/4 on the bottom the same as a 4 on the top? It just looks different. And then, so you'd square the 1/2, it'd become a 1/4. I could pop the 1/4 up to the top to be a 4, and then you square this, and that's that. So I could go one more line here, and I could force the 4 to the bottom like this. Right? And then this line here can turn into this line, and then we're done. Okay, that was a good exercise. Now let's do that problem that was the derivative. So I'm giving you an example of a function. Now you don't have to use the e stuff. You can just use the formulas from above in the table or the formula sheet that you can use on your tests. So y equals x secant hyperbolic of e to the x. And you're asked to find y prime. So we're trying to find the derivative of this. but I can use rules now. So what rule is going to be used here? Product rule, right? We have a product right here. There's your product. I was talking to another student about this earlier today. Some students came by to see me in my office. I encourage all of you to do that, especially for a class like this. If you're free before this class, I'm in my office from 11 to 1, but I've been getting there at 8:30. So if people don't start coming to my office, I'm going to start like going to the gym or something, working out or something, do something, right? But from 11 to 1, I'm going to be there. So I was talking to a student, and we were talking about in Cal 1, you have product, and you learn that when you have a product, the product rule, right? So let me just call on somebody that I don't know. How about Vanessa back there? Do you remember the product rule? Little? Okay, so go for it. No, it's okay. If you, like, is it derivative of what times what plus, do you, yeah? No? The product rule. Like, how would you do the product rule on this?
Yeah, it's
F prime times F. Okay, good. Show of hands. How many of you learned it that way? Oh, good. You learned it backwards. Hold on. All right, yes, but it does matter. I'm bringing up a point here. How many of you learned it a slightly different way? Okay, how did you learn it? Do you remember? Okay, so you learned F times G prime plus...
F prime G plus F times G.
Oh, F prime G plus F times G prime, like that, okay. Anyone learn it any other variation? We were talking, and someone else had learned it like this. I think it was FG prime plus GF prime. And a lot of people look at this and they think, okay, it really doesn't matter which way you learn it. They're all the same, which they are. They are all the same. You're going to get the same answer either way, because multiplication is commutative. You can always flip multiplication around. And addition is commutative, so that doesn't change anything. But there is a better way. There is a better formula, and this is the best one, and you can argue with me about it if you want. That's the best one. Because of this, the quotient rule is the exact same formula as that one, with a minus and a division by g squared. So if you learn the product rule this way, right here, all you have to do to modify it for quotient rule is add a minus and divide by g squared. If you learn it this way, then a lot of students look at the quotient rule and product rule as being completely different formulas, which can be confusing because you have to remember them. So my advice to you, and I just want you to see that when I do product rule, I'm going to use this formula right here. This is the one I'm going to use, F prime G plus G prime F. So when you see me do product rule on this, that's what I'm doing. All right, here we go. So what is F prime for me here? 1. So 1, I don't need to write it, times just the other function. Yes? I'm sorry? Who's asking what?
On the
Formula sheet?
is different.
What is it?
The quotient rule is different. It's g of x times f prime minus f times g prime over g squared.
And mine is this. Well, I'm not saying mine. I'm just saying another way. These, but they're the same, aren't they? Because commutative property of multiplication. But on the formula sheet, what's the product rule? I mean, yeah, what's the product rule on the formula sheet? Does it have it? What is it?
F times g prime plus g of f prime.
Okay, see, this is why I don't like this formula on the formula sheet. Because look, this is the one you said, right? These are the two formulas according to this author. This is the way that they choose to teach this product rule and quotient rule. So they give you the product rule, it's fg prime plus gf prime. That's what's in this textbook. But then they say, hey, to learn the quotient rule, it's gf prime minus fg prime over g squared. You see how you can, if you're first learning this, you can like really fumble this up? You know what I'm saying? Like, you've got to get, okay, wait, in the product it was the f, then the g prime, but over here it's the g, then the f prime. It can be confusing. Do y'all understand what I'm saying or not? Okay? Whereas if you just learn product rule the first time like this, then like I said, it's just a quick modification of that. Put a minus, divide by g squared, you're in business. All right. We still have a lot to do. All right, so that's the first part, plus now the derivative of secant hyperbolic, right, sorry, up here. The derivative of secant hyperbolic of something. So chain rule now. What is the derivative of secant hyperbolic of something? Negative secant hyperbolic x, tangent hyperbolic x. But for us, do we have x? No, we have e to the x. So this is going to be, what, a negative sign? So I'll put it in parentheses. Negative secant hyperbolic of e to the x, tangent hyperbolic of e to the x. Am I done? Times x. And that x comes from finishing off the product rule, right? Any questions?
Why don't you play e to the x? Like, why don't you take the derivative of e to the x?
Yeah. Where's that? Where is that?
Uh,
I didn't put it. I knew something was missing.
be next.
Y'all agreed, so I just kept, where is it? Right here?
Yeah.
So when you did the derivative of secant hyperbolic of e to the x, you got this, this. Then go inside, take derivative of e to the x. That pops out, and then the x. Glad y'all are paying attention. Now what? I mean, there's not a whole lot you can do with this, right? I mean, I noticed they both have a secant hyperbolic of e to the x. I could factor that out if I wanted to. But there's not a whole lot of more simplification that I could do. So I could do this, factor that out. Factoring out this term, I get a 1, and then I have a minus. I'm pulling this out. So all I'm left with is the tangent hyperbolic e to the x, and then the e to the x, and then the x. So I'm just going to put here x, e to the x, tangent hyperbolic of e to the x. There we go. We're done. So just a little product rule and chain rule in there. I almost messed up the chain rule. All right, next thing I'm going to show you I think is just super awesome. Did anyone have questions on this? All right, what I'm about to show you, in my experience teaching, it's almost 100% that nobody has ever seen something done this way. All right, so it's actually pretty exciting whenever I get to it. So we're going to talk real quick about the inverse hyperbolic trig functions, and I'm just showing them on the camera. All right. If we have 6 hyperbolic trig functions now, right? If we have 6 of them, they each have derivatives. We've talked about that. Then just like in pre-cal, we should have 6 inverse hyperbolic trig functions, shouldn't we? And I'm only going to look at 3 of them. All right? We're only going to look at 3. They don't come up that often, but these 3 do show up sometimes, so we should be familiar with them. And these are the definitions of the inverse hyperbolic trig functions: sine hyperbolic inverse, cosine hyperbolic inverse, tangent hyperbolic inverse. And those are their definitions right there. Pretty ugly. The hyperbolic inverse sine of x is natural log of x plus the square root of x squared plus 1 for all x in the reals. So as long as x is a real number, this is defined. So remember last class when we tried to define the inverse sine function, we had some domain restrictions. Same thing here. We have possibly domain restrictions for these inverse hyperbolic trig functions. For hyperbolic sine, there's no restriction. X can be anything. But for the hyperbolic cosine inverse, we have some restrictions on x. It has to be bigger than 1. Here, x has to be between -1 and 1. All right? So what I'm about to show you right now is example 3 here. I want us to show that the inverse hyperbolic of sine of x is the natural log. So actually show where did that formula come from. And this is cool. Yeah, my definition of cool is different than your definition of cool usually. All right, here we go. We're going to try and show that first one up there. So I'm going to start here with, I'm asking myself, what is sine hyperbolic inverse of x? Okay, that's what I want to know, right? And at the end of the day, I should have natural log x plus square root blah, blah, blah. So here's what I'm going to do, and just see if you follow me or not. I'm going to call this thing y. All right, I'm going to call it y. So I'm trying to find out what y is. Does everyone agree? If I can tell you what y is, and I have y in terms of x, so if I can somehow do something right now and get y equals and then something here that has x's in it, would you be satisfied that I've actually found a formula like that? Maybe? So I'm going to come in here and I'm going to take sine hyperbolic on both sides. Now we did not talk too much at all, in fact, about the cancellation property. Oops, I forgot the hyperbolic right here. That's a sine hyperbolic right there. But I should be able to do the same cancellation property that I had from last class, so long as there aren't any domain problems here. But what does it appear the domain restriction is here? There really is none, right? I mean, so we are okay to play this game taking taking the hyperbolic sign on both sides of the equation. So that leaves me with this. Sine hyperbolic y equals x. Now I'm trying to solve for y here, right? Trying to solve for y. And right now, I mean, I can't divide by sin h, right? That would just be, I get like beaten in a chamber in math hell for that. So I have to do something else. I need to release the y from the sine hyperbolic. And so I have no other choice right now but to just go with the definition of what sine hyperbolic of y is. So I'm going to rewrite this using the e's. So the left side of that equation, and Dustin, do you want to give me the left-hand side of this? You probably have it written down somewhere, hopefully. Okay, almost. It's not x, it's what here for us? E to the y minus e to the, right? I'll do 1/2 if that's okay with you. All right, so that's the left-hand side of that equation, right? Equals x. Now, I'm trying to solve for y, right? Trying to get y by itself. All right, I don't like the 1/2. You don't like the 1/2. Multiply both sides by 2. How about we do that? All right, so we don't have a fraction anymore. Now, I always like to give a student an opportunity to blow me away here. And maybe someone actually knows how to solve this for y. But I don't want you to be like, you kind of think you know and you're going to just wander around. I mean, like you either know or you don't here. So if you do, this would be a good time to raise your hand and let me know. Okay, that's a very good instinct to have. Yes and no, we're not there yet. The reason you can't do natural log, because you're thinking natural log is going to kill the e off, right? But there's 2 e's. Well, it's the way you bring natural log in, right? When you do natural log, you have to do it on both sides, don't you? So let's entertain the idea. It's not going to work, but let's entertain the idea. If I do the natural log of the left side, and I'm just going to say a minus b equals natural log of the right side, 2x. See, you cannot kill off these e's because they're separated by subtraction. You cannot distribute natural log to each one because natural log is not a number, so you can't treat it that way. And you cannot split this up into 2 logs because you can't split log into 2 logs unless this is what in here? Multiplication or division. So yes, but it's not going to work because we have 2 e's in there. That's a good instinct. Take the natural log. What do you mean?
Like, if you're essentially taking the natural log of y, then you wouldn't be canceling out the e.
I think that actually plays into the same thing. It's the way that you could bring natural logs in here, but it's the way that you have to do it algebraically. It has to be on both sides. So anything you do here, the natural log has to affect a difference, 2 terms instead of a single term.
Are you telling us to like add e on add e both sides and then not and then take the natural log? So it'd be
You're starting to get closer.
equals 2x plus e to the negative 1.
Say it again.
E to the y equals 2x plus e to the negative 1.
All right, I think y'all are starting to get there. It's not addition though.
Can you raise the whole thing to e to the y?
Both sides? Like raise like a power? I think what I'm interpreting is this. That's what you're saying. I don't know if that's what you mean. That's not what you mean? Okay, good. But you're close. All right, so we'd go all day. I just want to make sure that it wasn't like someone automatically that had it. Okay, like, oh yeah, that's obvious to me. You know? All right, so let's check this out. We're going to multiply both sides of the equation by e to the y. Multiply. Because here's what we really have, all right? I'll write it a different way for you. All right, that's what we really have. The e to the negative y really means this. Yes? Okay, now I'm going to multiply both sides of the equation by e to the y. And the idea is that I'm going to clear the fraction that way. But something else great is about to happen. So what happens when I multiply the left side by e to the y, and then right side by e to the y? So left side, what do I get? E to the 2y minus 1, right? Because this e to the y and that e to the y cancel out 1, equals 2x e to the y. Okay. So I have some fake money here for whoever wants to get that. Let me just show you. I mean, this is just, it's so cool because it's something you probably have never seen before. All right? So I don't want to waste time with you having to sit there and fumble over it or something. I don't mean that in a rude way. I'm just being honest. Because you could spend the rest of the weekend trying to figure this out. Okay, so I'm bringing everything over to one side. I'm trying to solve for what variable? Y. Okay, what I've done is I've created something that looks like a quadratic. Right? Kind of. It's kind of like I have e to the y squared minus 2x e to the y minus 1 equals 0. Isn't that really what that is? So if I just come in here and I just say, look, just for now, I'm going to replace e to the y with u. I'm going to make a substitution. Everywhere I see e to the y, I'm going to replace it with u. What would this turn into? U squared minus 2xu, right? Minus 1 equals 0. And here's where things can start to get even a little bit crazier. Because this is a quadratic in u, meaning u is the variable, right? But we also have another variable in there, right? X. How do you solve quadratic equations, usually? You try and factor them, right? But if it doesn't factor, what do you use? You complete the square or quadratic formula, right? I'm going to apply the quadratic formula to this. Okay, so let me remind you, because I really want to illustrate this. Here's what everyone knows, right? Everyone knows the quadratic formula looks like this. Right? That's the quadratic formula. If you have a quadratic equation, ax squared plus bx plus c equals 0, then the solutions are x equals what? The number in front of x, right? The number in front of x, change the sign, then plus or minus that number squared, then minus 4ac, and then all over 2a. That's how you do it. What we have here, I'm saying what is the variable here? U, right? So this is really like a u squared, u, right? So what's in front of u? See, we're used to having a b here, a number, aren't we? But our b is actually negative 2x. It's a variable instead. And a lot of people have never used the quadratic formula to solve for a variable in terms of another variable. It's always been a number here, hasn't it, usually? But I can still apply the formula. So the solutions to this are negative b. What's negative b? Plus 2x, right? The opposite of what I see there. Plus or minus square root. What is b squared? 4x squared. Minus what is 4 times a times c? Because a is 1, right? So 4 times 1 times negative 1. So 4 times 1 times negative 1 all over 2. Questions? U is equal to 2x plus or minus square root of 4x squared plus 4. Can I do anything to that? I can take out a factor of 4 out and then pop that out as a 2 out front, right? Can't I? So take the 4 out of both of those and then pop it out of the root. Oh, we're getting so close now. All right, u is equal to 2x plus or minus, I pop the 2 out. I'm left with, in here, because I pulled a 4 out, x squared plus 1 all over 2. Can I do anything else now? Reduce everything by a factor of 2? Oh, wow. I'm getting close, aren't I? X plus or minus. Now, I have a plus or minus. That one doesn't. And over here I have u. But wait a minute, what was u? E to the y, wasn't it? E to the y is this. And now you can come in with the natural log because you have e to the y by itself. If you do natural log now, it's automatic. It'll spit the y out. But you do natural log here and there. Understand? So, natural log on both sides. Natural log of e to the y equals natural log of x plus or minus square root of x squared plus 1. And the left side is really what? Y. So this is y equals this. Now, that's almost it, right? The plus or minus is a problem. What's that?
We set y.
We set what? Y, yeah, in the beginning we said arc sine hyperbolic, or hyperbolic inverse sine of x was equal to y. And I said, if I could tell you what y is later, then would you be happy? And so I've told you what y is in terms of x. The plus or minus is still an issue, though, because that says plus, not minus. Let's think about this for a second, all right? Just think about it. This is going to take a little bit more, I guess. You have to step away from it for a second, maybe come back to realize this. What can you not plug into natural logs? You can't plug negative numbers in, right? Natural log of a negative number doesn't exist. So is it possible that x minus this could be negative? Can x minus this be negative? Yes, but let's convince ourselves. Would you agree with me with this statement? X squared plus x is greater than the square root of x squared. Yes? Everyone agree? That left side's bigger than the right side because I'm adding 1 to it, right? Take this, add 1. So if you agree with that, then you agree with this. X. Right? Square root of x squared is x. Absolute value of x, but if we assume that x is positive right now. And now, what? Move this to this side. Look. This inequality says that if you ever have x and you take away the square root of x squared plus 1, it's always what? Less than 0. And that's exactly what we have here in the negative case. X minus the square root of x squared plus 1, we know that that's negative, guaranteed by this logic. So we can never have a negative there, can we? Or it won't work. So I better chunk that. And that's that. And the other two, you could get the same way. Isn't that I don't know, maybe it's just me, but isn't that a pretty awesome usage of the quadratic formula? I mean, you don't see that very often. All right, so we have some more derivatives. I don't know where the time goes. I'm not going to show this one because of time. This is a derivative, though. Okay, so look, I'm just going to walk you through it real quick. Oh, I should show my internet class what I'm talking about. I'm just going to walk you through this right here. If I wanted to take the derivative of cosine hyperbolic inverse, then what I would do is I'd come up to the definition of cosine hyperbolic inverse, which is right here, and I would take its derivative, which means I would take the derivative of a natural log. How do you take the derivative of a natural log? 1 over what's in there, then times the derivative of what's in there. If you do that, chain rule on that, you should get this result. And I'll let you do that yourself. But it's just, you're using that formula above, taking derivative using calculus rules. Now, the rest of the derivatives can be found in the book. I don't remember what page they're on, but they're on your formula sheets too. You should have a section in your formula sheets that has all the trig functions, all their derivatives, all the inverse trig functions and their derivatives, all the hyperbolic trig functions and their derivatives, all the inverse hyperbolic trig functions and their derivatives. That should all be on a sheet in your formulas, all right? So now know where to go to find it. But I want to talk about a very nice example. This is called a catenary. So if I were to take a look at the hyperbolic cosine function, we said it kind of looked like a parabola, right? Didn't we? Kind of looked like a parabola. Anybody know what a catenary is? I mean, I kind of give it away up there already. Okay, so if you take a wire, I need a volunteer. Let's see. Robert, thank you for volunteering. Here you go. If I take a wire and I hang a wire, let's just hang it like this, just like that. If we hang a wire, what is this shape? It looks like a parabola, right? But it's not. There's no quadratic function that you could lay right on top of this. There is, however, a function that does lay on it, and it's a catenary, and it's a cosine hyperbolic function. So what I want you to do, Robert, is put your end right there. I'm going to put my end right here, and I guarantee you it's going to be right on top of that blue thing. So there we go. If I tighten this up, let's see. See that? That's the only way it could possibly happen. So what happens if we move yours over a little bit? Then you say, wait, that's not it. So hang tight. Or Ivana, you can hold the other side if you want. So look, I'm going to change it. So what I'm going to do is I'm going to adjust the value of A. And that's going to adjust the catenary. So see if y'all can make that one happen. See? So every hanging wire, no matter how you do it, can be modeled with a hyperbolic cosine function. So they're very important because you can let it go. Thank you. That's all I needed. Is that somewhat convincing that that function works for the hanging wire? All right, hopefully you're convinced. So what are the things that we would want that for? Why would we want to know the graph, the function that, you know, gives you a hanging wire? Just because that's fun to know, or what?
Do you ever have to hang wire?
Yeah, what if you have to hang wire?
Maybe building suspension bridges.
Yeah, if you're building a bridge. You know it's a cosine hyperbolic function. So here's a specific example, all right? Let's say that we have a catenary that looks like this. We have a pole, here's the ground, another pole here, and we're hanging a wire between them, like this. Okay? There's our catenary right there. And we can show that if you look at the lowest point on the catenary here as being the middle, and you measure out to the first pole, let's say it's 7 feet to that first pole, that we have modeled that red catenary to this function. Y equals 20 cosine hyperbolic of x over 20 minus 15. So the minus 15 on the end, I didn't show you what that is. That just moves your catenary up and down. Okay, so if you want to put it on a taller pole or a lower pole, okay, so that's all that does. Okay, so this is the model of that red catenary. Got it? Here's the question. I want you to find the angle between the red catenary and the pole. The angle. Because look, there's forces involved here, right? There are forces. The mass of the wire is, gravity, and that's pulling the poles in, and the mount that I have that's holding that red wire there has to be strong enough to hold that force, right? I mean, got to build it, engineer it properly. And so I need to know the angle that is going to be pulling on that harness, that connection. I need to know what that angle is. Because we all hopefully know that it's different if you pull on something straight as opposed to pulling out on an angle. The forces are completely different. So knowing that angle is important. How are we going to do it? Anyone have any ideas? I won't call on anyone. So the question I'll put up here, find the angle between wire and pole. You might be asking yourself some questions like, what does he mean by the angle between wire and pole? Like, where are we talking about? What angle? Are you thinking that? Like, okay, you're on to it, Ron, right? Ron, am I right? See, I learned at least your name for today, and I'll forget it. Okay, so Ron is suggesting that we find the what? The derivative of the wire. The derivative represents the what? That's other way. First, the derivative from Cal 1 represents the slope of the tangent line, doesn't it? So Ron's suggesting that we find the derivative, which would represent the slope of this line, and you said as close as we possibly can to that point, right? So you want to go as close as we possibly can? Okay. Can we actually go to that point? Can you find the derivative of a function at a point? Sure. So if we actually pick that point right there, and we find the slope of the tangent line, that will form an angle, theta, won't it? That's exactly the way we want to look at it. So that means you're going to have to first figure out what the slope of that blue line is, which is the derivative of that function at what point? At 7. So let's take the derivative of that first. What is the derivative of that? All right, what about the 20 in front? Just leave it, right? What's the derivative of cosine hyperbolic of something? Sine hyperbolic, right? Of that something? Am I done? Derivative what's inside? What's the derivative of 1/20th x? Because that's what x over 20 means, right? What's the derivative of 1/20th x? 1/20th. So we need to tack that onto the end. And then we're done with chain rule on this. Derivative of negative 15? 0. So this is it, right? And I think our 20 and 1/20th cancel. So all we get is the hyperbolic sine of x over 20. Are you all with me? Yes? Now, if I could tell you now the derivative at 7, that would give me the slope of that blue line. So the derivative at the value 7 is equal to sine hyperbolic of 7 over 20. Now, your calculators do a lot of times have the hyperbolic trig functions on them. But let me remind you of another way you could compute this. It would still require your calculator. 1/2 e to the 7/20ths minus e to the negative 7/20ths. Right? So what I'm doing is, this is hyperbolic sine of x. And so we know that that is 1/2 e to the x minus e to the negative x, replacing x with 7/20ths. And what I would like for you to do is on your own, you don't have to do it now, make sure that you can plug this into your calculator and get the correct answer out of this. You should get about 0.35712. And I rounded that last digit. And I'm going to go out 5 decimal places here. 4 or 5 decimal places. Now, am I done? What does this quantity represent? The slope of that tangent line. What is the question asking? The angle between the wire and the pole. Is that slope the angle? No, the slope's not the angle. How are you going to get that to an angle? Yes?
When you extend the line of the slope, is it going to meet at the 0?
Nope, doesn't have to. What is slope by definition? Rise over run, right? So let me help you with this. We want to know what theta is. Do you agree? All right. And what we know is this slope, rise over run. So if I take that triangle right there, and I draw that triangle a little bigger so you can see it, and here's the pole, and we're trying to figure out what theta is. If I tell you I'm going to stop this triangle somewhere, right? It goes down, I could keep going, right, with it. I'm going to stop it arbitrarily when this side is 1. Then what is this side? 0.35712. Because you just told me that slope is rise over run, right? And if I write this way, rise is this, run is this, rise over run is this, right? I'm just cleverly using 1 here, and that forces this side to be this. Understand? Can you give me theta now? What's the trig function that connects theta to those sides? Tangent. I know that tangent theta right now is what? Careful with where that theta is. 1 over 0.35712. Right? Tangent is opposite over adjacent. So I have to turn my head opposite over adjacent. If theta was down here, it'd be different, right? Then I would do that over that. Okay, so someone tell me what I can do now, because I'm trying to solve for theta. Arctan on both sides, good. So if I take inverse tangent on the left side, I get theta. What I do to the left, I have to do to the right. So who's going to give me the answer off their calculator? And make sure you know what mode you're in, because I want the answer in degrees if possible. So make sure you're in degree mode.
70.35.
Yep, 70.35 degrees. Approximately. We're rounding here, but that's good enough. So the angle at that point is 70.35 degrees. Pretty good. Well, I thought we'd get to 4.7 today, but we didn't. We have a couple more minutes. I'm just going to put a couple of problems up here for you to try until time runs out, right? These are derivative problems. Just practice taking some derivatives. Your homework. I've changed the homework assignment a little bit, so if you printed the notes off the web, what's highlighted in yellow is additional. 48 I planned on doing in class today, so what I'm going to do is just say that 48 is going to be a bonus question, all right, to be turned in at the beginning of class next time. So 48 is a bonus question to be turned in at the beginning of class. And because I didn't do 48, 49 relies on 48, so you can kind of scrap this, 49, all right? Everyone understand? 48's a bonus? Mm-hmm. Okay. Both of these, find the derivatives. These are not designed to be like nasty problems. It's just basic differentiation. So if you can do those, you're free to go after you're done, or if time expires here. Anybody need to sign in? Anyone? Yes? Initial. What's that?
I didn't realize homework was training.
That you didn't have to turn it in? Yeah. I can't imagine trying to grade all of your homework. I think that would be kind of hard, right? But on the other hand, students who don't usually do their homework usually aren't here to talk about exam 2, so. All right, y'all go ahead. I know y'all want to get out of here, but see if you can at least get these two. I'll put the formulas up here for you. There. Those are the only derivatives you need for this. Don't turn these into e's, okay? Go off of that. So derivative of tangent hyperbolic is secant hyperbolic squared, and just go straight with that. A lot of the E stuff I did today was just to get you used to that sort of math. I mean, that's, as you progress through the engineering fields, I mean, all that stuff you saw, I mean, that's just natural, comes with the territory type of stuff.
So you don't want us to put the E all the way.
Unless it says, like, prove this identity, then you have to do that. Other than that, it's use the formulas. That's what they're there for. All right, I'm going to shut this camera off.